Welcome to the Greek Ship Corrosion channel. My name is Maryam. I'm a researcher in the field of corrosion and protection of materials. Chapter 8, Section 1, Electrochemical Impedance Spectroscopy. Basics of EIS in studying corrosion behavior of metals and alloys. Advantages of sine wave, Randles cell, and Faradic reactions are discussed in this video. Electrochemical impedance spectroscopy offers kinetic and mechanistic data of various electrochemical systems and is widely used in corrosion studies, semiconductor science, energy conversion and storage technologies, chemical sensing and biosensing, non-invasive diagnostics, etc. This method for evaluating of corrosion rate and mechanism is based on measurement of alternating current impedance over a range of applied frequencies. The method is rapidly expanding due to the development of applicable instruments and capability of the method in providing additional information on the corrosion process and electrochemical cell performance. The method normally involves application of time-varying small potential excursions about E-core or corrosion potential, measurement of external current or IX, and determination of the system impedance Z and the impedance phase angle delta. Solid wave is potential excursion and dotted wave is external current. The angular frequency equals 2 times pi times frequency. The applied AC potential E experimental minus E core is normally sinusoidal as in this figure. At each frequency, the measured external current IX may be out of phase with the applied potential. This phase difference is due to physical processes that behave as capacitive or inductive elements rather than resistive elements in an electrical circuit considered to be equivalent to the electrochemical cell. Omega T is equal to 2 times pi. Consequently, the system impedance Z also may be out of phase with the applied potential. Delta is the phase angle between the impedance and the applied potential. These quantities are determined as a function of applied frequency. To obtain maximum information, the Z and delta must be determined over a wide range of frequency. Corrosion and electrochemical phenomena are interpreted in an equivalent electrical circuit in which each electrical quantity relates to the electrochemical, chemical, and physical processes associated with the cell. Advantages of sinusoidal excitations. 1. Sine and cosine waves are fundamental periodic waveforms that can be used to construct any complex wave shape through a process called Fourier analysis. Xt equals A times sine omega t, Yt equals B times sine omega t plus theta. System function: if J equals the square root of minus 1, H omega equals the absolute value of H omega times exponential of J theta. If Xt is current and Yt is potential, then H omega is the impedance. 2. Alternators simply produce sine wave naturally. 3. Sinusoidal signal is the smoothest signal and form a basis function. 4. Basis function means every other continuous periodic function can be expressed in terms of sines and cosines. For example, triangular and square wave can be expressed in terms of fundamental sinusoidal frequency and its multiples according to Fourier series. 5. The response to a sine excitation is always sine. 6. Many functions can be expressed as collection of sine functions. So, if we know the response of an electrical circuit to a sine excitation, we can find the response of this circuit to any other excitation by superposition. Randel cell. The Randel cell is the simplest equivalent circuit for EIS analysis. It includes the solution resistance Rs, the double layer capacitance CDL, normalized with respect to the specimen area, and the charge transfer polarization resistance RCT or RP. Rs is normalized with respect to specimen area, is the solution resistance between the working electrode, corrosion specimen, and the reference electrode. A Randel circuit may consist of an active electrolyte resistance Rs in series with the parallel combination of the double layer capacitance CDL and an impedance ZW of a Faradic reaction. Often a constant phase element CPE replaces the double layer capacity. Faradic reaction. Electron transfer causes oxidation or reduction to occur. Since these reactions are governed by Faraday's law, that is, the amount of chemical reaction caused by the flow of current is proportional to the amount of electricity passed, they are called Faradic processes. Faradic process versus capacitive process. Faradic and non-Faradic processes take place in a working electrode. Faradic processes generate currents through the redox reaction on the working electrode surface. Non-Faradic process is known as a no-charge transfer reaction in the electrode, a capacitive versus Faradic reaction. Electronic charge, hydration shell, Stern layer, ionic charge, and in Faradic reaction, electron transfer occurs. Ionic charges in the non-Faradic process stay on the working electrode surface, which leads to the charging and discharging of a double layer capacitance. Example of a Faradic process. In this figure, left-hand electrode shows oxidation of water to H2O yields O2 plus 4H plus 4 electrons at LHE. At right-hand electrode, reduction of water occurs. 4H2O plus 4 electrons yields 4OH minus plus 2H2. Uncompensated resistance. Electrochemical test cells always have a solution resistance controlled by the cell's geometry and the composition of the cell's electrolyte. Current flow through this solution resistance can cause significant errors in the cell's measured potential. In this Randel's cell circuit, R omega is uncompensated resistance, Rp is polarization resistance, CDL is double layer capacitance. Compensation of the solution resistance. A 3-electrode cell compensates some of the cell's solution resistance through placement of the cell's reference electrode. Because reference electrodes are not infinitely small and they cannot be placed infinitely close to the working electrode, this compensation is always incomplete. The portion of the total solution resistance that is left uncompensated is called Ru, or uncompensated resistance. Counter electrode, reference electrode, working electrode. Luggin capillary. Luggin probe assembly is used to place the reference electrode as near as possible to the working electrode for decreasing of uncompensated solution resistance. This is the Luggin probe. Thank you for your time and attention. Challenge number 24. If you like to challenge yourself, please answer this question in the comments below. 1. What's a potentiostat? 2. What is a frequency response analyzer, or FRA?